Hello world, here's Jorge and let's continue learning about object detection in PyTorch. In the last video, we finished our init constructor. More specifically, what we did was to define the block pool layer. So essentially a layer that was able to average over multiple gradients, and within these gradients, we were not taking into account the negative direction. All right, so just taking into account the number of orientations. Then we also define a padding layer, and finally we define the glyphs. Okay, to basically finish with the render layer. Okay, and well, what I just did was to implement it in the constructor. The code is essentially the same that we discussed. Okay, great. So now let's continue. And to do that, we are going to talk about oriented gradients. And well, more specifically, we're going to define a function that is going to be able to take a 4D tensor. Okay, that is the usual shape of number of batches, color channels, height and width, and is going to be able to output oriented gradient. All right, that means that essentially we are going to compute the whole gradients. Okay, so both taking into account the horizontal gradient and the vertical gradient, and out of these whole gradient, we are going to be able to compute its oriented gradient. So that meaning that once we compute the gradients, we're going to be able to say pass it through the orient layer that we defined in our init constructor, and we are going to be able to classify all the gradients depending on its associated angle. That meaning, for instance, in this problem, we define number of orientations to be equal to 9. So that means that our gradients are going to be distributed in the following regions. So from 0 to 40 degrees, from 40 to 80 degrees, and so on till 360. Okay. So these orient layer, passing our gradients through these orient layer, is going to be able to classify our gradients with respect to its associated angle. Okay, so that is what this function that we're going to call compute oriented gradients is going to do, and of course also it's going to output the magnitude of the gradients. All right, so let's explore how to do that. And to kick off, we are going to essentially remember the definitions that we have for our gradient filter weight D and our gradient filters, more specifically the horizontal gradient and the vertical gradient definitions for both grayscale images and RGB images. Okay, and of course these code what did was to just overwrite the weights as we specified in our definition of D. Okay, great. So now to start with, we are going to define a random tensor, because what we want to do is to test our function, and then say start defining it to then implement it within our HOGnet definition. Okay, great. So let's start with a random tensor, and say just toss around, and let's define it in a very simple tensor. Okay, let's start with grayscale. Just grayscale. As you'll see, we're gonna define in our function so we're gonna set a if-else statement, that meaning that if our image is grayscale, some part of the code will execute, and if it's RGB, the other will execute instead. All right, so let's just start with grayscale now, and say a very simple image, of course. Yeah, simple as I can imagine, a 2x2, right? just to check. So, and now let's print the result just for the sake of clarity. Tensor, not image. Okay. All right, here we have our 4D tensor, 1, 1, 2, 2 shape. Great. And what could we do now? Well, we want to test. We want to test our layers on this tensor. That meaning we want to do some forward pass on it, right? So let's start with again, we are dealing with grayscale, right? So we need to select one of these two, either the horizontal gradient layer or the vertical gradient layer. Let's start with horizontal, say. And what we can do is the following. We can do, okay, so du pass, and say, yeah, let's just call it du pass. And now we're gonna pass through our horizontal gradient layer du. We're gonna pass our random tensor and see what we get. Let's print the result. Okay, great. So as you can see, this is our original tensor. Okay, our original random tensor, and this is the result of passing the say du of passing our tensor, I mean, through our du horizontal layer. All right, great. So that works perfectly. So now let's test our RGB. Okay, let's test our RGB, and to do that, let's comment this out, and let's do the analogous for the RGB, one of the two, say the horizontal. Okay, so RGB, and what we can do is just to pass, and of course now we need to select the du RGB horizontal layer. Okay, du RGB, and we're gonna pass this random tensor. Okay, let's see how it looks. Fantastic. So now you see that we start again with well, let's think about what just happened. I mean, is this correct? No, really, because well, we're dealing with a 3D, so a 3-color channel, I mean, okay, image, but here I just stated one, so this is not correct. We need to state that we're dealing with a 3-color channel image. Let's see. Oh, okay, what happened here? Because before it worked and now it doesn't work. Okay, let's think. Given group 1, weight of size 3113, expected input one channel, but 3 channels. Let's think. Well, first of all, it's saying you gave me groups equals 1. Okay, so if we go to the horizontal layer, we see that indeed we gave him groups is equal to 1, right? Because remember that for cont2d, okay, for cont2d, we had by default groups is equal to 1. So if we don't specify otherwise, that's going to be the value, right? So that's what just happened here. But again, remember, if we leave it like this, this is not going to be one-to-one mapping. That meaning that we want to assign one group to just one layer, one color channel, right? So we definitely need to modify this. And actually in the original code, we stated here groups is equal to 3, if you remember, okay? So that's what we need to change, and that is why previously it worked, because we set this value to be equal to 1. So the output indeed is going to be 1, but this is not what we want for our color channel. So indeed, what we need to modify here is just adding groups equals 3. Yeah, so this is why it's important to pass, say, dummy tensor through our layers in that way, very simple way, to see if we basically have a correct operation going on before we start defining the function. So, alright, so this should now work. Now we have 3 color channels, we have 3 groups, 1 per channel, because we have 3, 3, and then 3 groups, 1-to-1 mapping. Fantastic. So now this should work. Let's see. Fantastic. You see, now we have a 3 color channel image, and as a result we get 3 color channels too. As a result, I mean, of passing our random tensors through the DU RGB layer. All right, great. So now we solve this this problem, and now we're ready. We're ready to start with the actual definition of the function. Okay, so let's just comment this out and get started. And yeah, just for reference, let's actually print this out. So we're gonna do original tensor, right there. Fantastic. So now let's get started. So let's define the function, and let's go ahead compute oriented gradients. Well, as originally stated in the practicals, okay, of VGG. So gradients, and the input is just going to be the image, in this 4D image. Okay. Well, let's just remember that we said that we're going to define 2 blocks, and let's start with the simplest, the grayscale. Okay, so what we're going to do is just now pass a grayscale image to our function. Okay, so first of all, well, we need to define these 2 blocks, right? So how to do that? Well, if statement. So we're going to say if our image has dimension equals 1 in the color channel slot, we are going to execute this code, right? So to do that, we just need to access the index 1 of our image. So to do that, we just do dot shape, and the index, well, remember that this is a tensor, so we need to access through brackets. Okay, great. And this is going to be equal to essentially 1, indeed, because this is the grayscale. Yeah. Okay. Now what we need to do is, first of all, well, do the pass. Okay, we're gonna do the pass. So that means that we're gonna compute the horizontal gradient for the grayscale image. Okay, so compute the grayscale horizontal gradient. Okay, great. And well, we're gonna just say du pass, and this is going to be equal to well, as we did before, du, and we're gonna pass the image. Great. And just for the sake of clarity, let's include here a print statement. So let's say we just did a well, so this is the horizontal grayscale gradient. Okay, fantastic. And let's put here space, Fantastic. So let's have a look. Let's have a look. Oh wait. Oh, of course. First of all, let's put here a space, and here a space too. Fantastic. And also, what I want to do now is, of course, if you don't call a function, nothing's going to happen, right? So, compute oriented gradients, and we're going to call the actual random tensor, the image. So, great. Let's do it. Fantastic. Now, yes, this is the original tensor, and this is the result of passing the horizontal, so basically passing our tensor through the horizontal layer, the horizontal gradient layer, okay, which yields the horizontal gradient. Fantastic. So now, what we're going to do is to do the exact same for the vertical. Remember that before, when testing, well, I didn't test the vertical because it's completely analogous. So, but now we need to include it in our definition. So now we're going to compute the vertical grayscale gradient. So we do the exact same thing. And now vertical instead. Great. And this is going to be dv. Okay. And this is vertical, of course. Great. So now, fantastic. We also got the vertical gradient for the grayscale image. Fantastic. Now, what is next? Well, we can compute the magnitude of the gradient. All right. Once we have the two components, we have everything we need to compute the actual gradient, the magnitude. So to do that, well, magnitude of the gradient. Okay. So to do that, well, we're going to call it n. And yes. So what we can do is just multiply. Just in regular mathematics, as we do in regular mathematics, just it's going to be the square root of d squared plus dv squared. Okay. Great. Now, what can we do? Well, let's think about this, because there is a detail we need to discuss here. Well, it turns out that in computer vision, it's actually quite common to work with the square of the magnitude instead of the actual magnitude. And so that means that we're not gonna say place here the square root, okay? But I've been thinking on why this could be the case, and my interpretation is that when we have especially high gradients, okay, that meaning gradients that are very close, well, above 1, okay, what happens is that when you square it, then you're gonna say strengthen, or you're gonna increase its value more as when you compare it with when you take the square root, okay? So what it's doing is that taking the square of the magnitude is emphasizing, or it's amplifying larger gradients. And if you think about it, in this particular context of object detection, what we're doing is we're interested in detecting strong edges, okay, and transitions from one region with a very high gradients as compared to one neighboring region which has quite low gradients. So hence, to detect these say strong variation, it makes sense to take the square of the gradient, because it's going to highlight even more the gradients that have especially high value. All right. Instead, if we were to take the square root, the values of the gradient that are especially high would get lower values as compared to taking the square. Okay, so that is why. That's my interpretation. Please feel free to comment yours if you got any different. I'm always open to learn. And that is why we're going to take instead the square of the magnitude of the gradient. Okay, so let's just state just to state that this is a square. I'm going to place here an n2. All right, and also we're going to actually print the result. So let's state here that this is the squared. This is squared magnitude of the grayscale gradient. Great. This way. Fantastic. So great. There we go. Again, these are random, and in this particular case, we didn't get one that is above 1. Let's see if we can get one. It doesn't. No, it doesn't matter. But yeah, essentially, the reasoning is what I just discussed. Okay, of why we're taking the square. Great. And now let's move on, because this is the part of the code that is going to execute if we get grayscale image. Okay, so well, what happens if we get 3 or RGB image instead? Okay, what's going to happen? Well, so we're gonna need to define another block. Okay, and to do that, well, let's start now by just changing the color channel to 3 so that we execute the particle that we want to assess. And well, what do we do? What do we do now? Well, completely analogous as we started. So we're going to start the same way that we started the first block. We're going to define a path. All right. And again, notice that if the second part of the block executes the first dozen, so what we can do is to just use the same variable, the uPass and the vPass. So that's what we are going to do. So let me just take this, and now we're going to compute is RGB instead of grayscale. And now we get RGB here, and same story for the vertical. So RGB, and we're going to have here. Well, this is horizontal, yes. RGB. Okay, fantastic. And we're gonna get, so I'm gonna print out the vertical result. DB here. Fantastic. Great. Yes. So yeah, we just computed our both horizontal and vertical RGB gradients. But now what could we do? Well, completely analogous. Now we also take the magnitude of the gradient, okay? So again, we are going to do this essentially. Okay. So the magnitude of the gradient, and now, well, nothing changes here because remember we're using the same variables. Fantastic. So now what could we do? Well, first of all, let's change this to RGB. And now what we're going to do is to take the maximum values of the essentially magnitudes of the gradients. Okay, because remember, what we want to do is to collect the highest values, the highest possible values of the gradients, because those are the ones that have the most important features, okay, for our model code. So to do that, we're going to use torch.max, okay, torch.max, and let's first understand how it works. So torch.max, there we go, great. So this is going to return the maximum value of all the elements in the input tensor. Okay, so well, this is a simple example, but here you see that we don't specify the dimension that we want to act upon, right? So let's actually see an example that does. Okay, this one. So, well, the dimension, you see the dimension to reduce is the dimension that we want to reduce, okay? So essentially, here we start with 4D tensor. Well, no, a 2D tensor with a 4x4 matrix. And what it's stating here is that we want to take the maximum and that we want to reduce the dimension 1, that is the dimension of the columns. What does that imply? Well, that implies that we are going to essentially take the maximum values of the rows. Okay, we're going to take the maximum values of the rows, and we're going to store them as well, here, as you can see, just a line tensor. Okay, so, and indeed you see how a dimension was reduced, because we started with a 2D here and we end up with a 1D. Okay, so as you can see here, what it's doing is just storing the maximum values of the rows. So this one, this one, this one, and finally the one that is in the index 1, or the last row. Great, and but notice as well that we get a tuple. Okay, as an output we get a tuple, and so the first element of the tuple is the result of the maximum values of the tensor with respect to the dimension that we reduced, and the second element of the tuple are the indices. Okay, so we get index number 3, index number 0, 0, and 1. Fantastic. So now we have an understanding of how torch.max can work, but let's actually see it in action. That's the best way to understand how it works, right? So just let me start with the print statement here, so that we can see how it works and how are we going to apply it for our problem. Okay, let's think about this. So torch.max, what is the input tensor? Well, the tensor with the square magnitudes. Okay, what dimension do we want to reduce? Well, we are gonna do the columns, that meaning that we're gonna scan through the rows, just as we did with the example in the PyTorch documentation. And what else? Well, let's actually look at these other documentation, and okay. Well, actually, something that we can specify. It's not. I think it's not. Oh yeah, it's here. So keep dimension, whether the output tensor has dimension retained or not. Okay, and default is false. So what it's doing is to keep the dimension of the of the original tensor. But let's see how it works. So we want to keep the dimension. Okay, so keep dimension true. Okay, great. And let's see how it looks. Okay. Well, first of all, we get a tuple, of course. We'll deal with that later. And as you can see, we get, well, the first element of the tuple is actually the tensor with maximum values, and the other element is just the tensor with indices. All right. So let's see what is going on here, because this example is a bit trickier than the one that we saw in the PyTorch documentation. Okay, so let's think about this. Well, this is our input tensor for the maximum, for the torch.max, and we get this output. Okay, so what is going on? Well, remember that we're going to be scanning through the rows, but how do we do that really? Well, remember that here we're dealing with 3 color channels, so each channel has its own tensor associated to it, right? So how is that working? Well, so remember that for each pixel we're going to have a contribution of each. We're going to have a contribution of each channel. So for example, the pixel 00, right? So the one at the top left. So that pixel is going to have a contribution from this color channel. Is going to be 00247. Then the contribution of the middle color channel is going to be this one, and the top left, corresponding to the third tensor, is going to be this 5707. Okay, so what we want to do now is to actually be able to identify the maximum value of those 3, because what we want to retain is the value that corresponds to the channel, right? That is essentially higher. Okay, that is what maximum torch.max is going to do. So, for example, if we look at the pixel 00, indeed, what we get is that the second channel is the one that has a pixel value that is higher. Hence, we keep that value. Okay, that is indeed what's happening. Then, what happens with the, say, 01 pixel, right? So we have these 3 values, and well, the higher value is this one. So indeed, that's the one that we retain. Fantastic. And completely analogously, we understand that this is the value that needs to be retained for 10, indeed, and same for these, say 1. Fantastic. Great. And as you can guess, now the corresponding indices are actually associated to the position of this actual maximum value of pixel. Okay. For example, yeah, again, we're done with 08207, so that corresponds to the color channel 1, because this is the color channel 0, 1, 1, right? So it just turns out that in this random example, we get all of them in the second channel. So in this particular example, only the pixels that correspond to the second channel, or the one in Python, say indexing, would be contributing. Okay, but just so that you see that was just by chance, let's just execute here. Okay, so you see now that is only the second, so the last channel, the one that has the higher values. All right. But yeah, now we understand perfectly how torch.max is operating, just extracting, just keeping the maximum contributions of each color channel in terms of gradient. Okay, magnitude of gradient. Fantastic. So now what we want to do is to say, yeah, let's just first of all, state some print, just print out some statements so that is everything more clear. So what we can do, well, no, actually, first of all, that, because think about this now, we have, because naturally the torch.max yields a tuple, okay, as a result, but we want to organize this better, okay? So to do that, we're going to define a variable for each result so that we can then manage them much easier, okay, later on. So what we're going to want to do now is, okay, we're going to store, I'm going to rewrite n2, right? Because the point of n2 is just to get the maximum gradient magnitudes, okay? Hence, now that we extracted actually literally the maximum, then we rewrite n2, okay? n2, and then let's call the other one indices. Fantastic. And we're just gonna equate this to torch.max, because in that way we're gonna just get the say results systematically. Okay, so I can actually comment this out now, and let's write this print statements now. Yeah. So print, and we're gonna state that the maximum. So maximum. So, or better say, maximum contributions of color channels so maximum contributions of gradients. Let's say maximum contributions so maximum contributions of color channel gradients, yeah, let's call it like that. And let's just say in 2. And now let's also print out the indices. The corresponding indices. To maximum color channels, or maximum you could call RGB gradients. Yeah, let's put RGB here. And here, and this is fantastic. So now you see that instead of having all, say on screen a bit disorganized, now we have it better, like more cleaner, and store each in a specific variable. Okay, great. So now we can continue, and yeah, we can just continue now. And how can we do so? Well, what we're going to do now is to introduce the concept of gathering. All right, we're going to do that. And before going to jump into the function itself, let's go outside and understand basic example of tortoise gathering. Okay, so let's do that. So just a simple example. Okay, and so what we can do is, well, first of all, let's have a look at the PyTorch documentation. So gather, tortoise gather. Great. So now, so what does tortoise gather do? Well, it gathers values along an axis specified by a specific dimension. Okay, so what does that mean? Well, here we have an example. So actually, let's go through this example to understand it. Okay, so I'm just literally going to copy that example. Okay, so this tensor is going to be 2 by 2 tensor. Okay. One, 2, and 3, 4. Okay, just to visualize it, let's see. Fantastic, I choose the tensor, and actually print this for comparison later. Okay. All right. So how does torch.gather work? Well, let's think about that. Let's first actually say I'm just going to execute this so that we see the result and then explain. Okay, so we're going to have torch.gather, input the original tensor, then this one. Now we'll discuss what that is doing, right? Then we introduce an index tensor. Okay, so we're gonna have torch on tensor, and it's going to do the following. Okay, so 0, 0. I'm just copying the original tensor that is given there. Okay, 1, 0. Okay, so let's see what these yields. Okay, so we got this. All right, so what's happening? Well, here we need to understand. So let's go through it slowly. So here we have an input tensor, right? And then this value here, what does that do? Let's actually visualize that. This one is the axis along which to index. Okay, so well, what does that mean? Let's see that through an example. So we're gonna index through columns. That means that we need to look at the values that are stored in the columns and compare. What do I mean by that? Well, let's actually start analyzing the first row of the original tensor, that is T0, right? So T0 actually in this case is 1, 2, yeah, is 1, 2. Okay, that is the first row, and we need to actually now have a look at the first row of the index tensor. Okay, this tensor. Does it have a specific name? Let's call it index. And again, first row. Well, what the row is 0, 0, right? Okay, so what is this torch.gather doing? Well, it's taking the first element of the first row, okay, and then what it's doing is, okay, go to the corresponding value in the columns of the first row of the tensor, of the original tensor. Why the first column of the row? Because we are indexing with respect to the columns. Okay, so it would be in this case 0, right? So 0 corresponds to the first column of the first row of the tensor t, that is 1. Okay, so that means that this is the value that needs to be gathered. This is the value that needs to be stored in the resulting torch.gather. Okay, so that is why we see here a 1. Then in the second, let's go to the second column of the index. Again is a 0. This means that again, when we go to the corresponding row in the original tensor, again we need to take the first value of the column, okay, because it's a 0 again. So again, we're going to see here a 1. All right, fantastic. So we need to apply the exact same logic with the second row of both tensors. Okay, so we're going to have here 1, and we're going to have here 3 and 4, and here we have 1 and 0, right? So again, we need to have a look at the, well, this one, of course. We have a look at the first index of the first, so basically the number that is stored in the first row and a first column of the index tensor is 1. So this means that we need to look at the second column of the second row of the original tensor t. This is a 4. That is why we have a 4 here stored. Yeah, and again here we have a 0, and in the 0 we're gonna actually have to store so the corresponding value. In this case is going to be well, this 0 is going to be again the 3, right? So that is why we get it 3. But now we understand why, how it's working with respect to the column. So what happens if I just put here rows, right? Oh, what happened here? Let's see. So, so the logic should be completely analogous, but now with the rows. Okay, so 0, right? A 0 corresponds to the first element, so it should be indeed a 1, and now we get a 0 again. So yeah, indeed, what we need to do, well, actually, let's just stick for now with the columns, because what we're going to do now is working with the, let's actually first understand perfectly how columns work. So essentially, let's actually change now these. So this 0, say I change it to 1, right? To check our understanding. Well, now, well, we get the same results in the first row because we didn't change these. But what happens now is that now we have a 1 here. We have a 1. So this 1, again, is going to refer to these. So now to these value, because it's the second column, right? So now what we are going to have is a 4 here. Okay. Instead of a 3, because we changed the index. Fantastic. So now we understand how it works with columns. And now we're going to go back and apply it to our own problem. All right. So let's see. Okay, so now let's do the total gather, and let's see how. All right, so we're going to need to do this gathering for both du and dv gradients. All right, so I'm going to call, well, actually, yeah, let's call it du gather. Okay, du gather, and this torso gather. And let's do here, well, what is going to be our input tensor? Well, du pass. Okay, du pass, and we are going to operate in the same way that in our example, that is with respect to the columns. All right, and now what is going to be our index tensor? Well, of course, the one that we obtained previously. Okay, so all right, and now let's have a look. Let's have a look. Let's print this. Okay, and let's, yeah, just call it gathered horizontal gradient. Okay, fantastic, and just call here du gather. Okay, let's see what happened here, because we want to understand how this our actual case is working, right? So to do that, let me here print again, just for the sake of comparison, the easier comparison, the input tensor du pass. Okay, all right, yeah, just put it here. Okay, and compare. Okay, this is the input tensor. Okay, this is a resultant tensor, and these are the indices. Okay, well, wait, yeah, these are the indices. So what is going on? Well, what this is telling, so the gathering, what it's doing is, based on the indices, that is given is going to store the corresponding values. Okay, so in this case, what is happening? Well, remember that now we have 3 color channels. So we need to be comparing with the corresponding pixels to, so the pixel that corresponds to the channel, okay, and compare basically pixels that have or that are stored in the corresponding location. Okay, so let's start with the 0, 0, and given that the index that is input here is 0, yeah, then the index that corresponds to that value in that specific pixel is the one that's going to be stored. So for example, in this case 0, so it's going to indicate that 0.2140 is the one that is going to be stored. Okay, great. So now what happens with the set? Well, number 2 means that this value is going to be stored. Fantastic. And then this 2 here, fantastic. Again, we need to store then this one. Fantastic. And completely analogous, we have here the 7301 as expected. Great. So now we understand how the gathering is working, just storing the value within, say, the channel that corresponds to the given index. Great. So now let's just continue. Because I did this for the horizontal, but we need to do the exact analogous, and let me actually comment this out. We don't need this anymore. So what we want to do is completely analogous, say, analysis for the DV gather instead. All right. So let's do that. DV gather. And this one is the vertical. Great. Okay, so we have the vertical, we have the horizontal. Okay, why? Yeah, of course, it's giving us the same because I need to place here DB paths. Great. Fantastic. Now is okay. Great. So now what we can do is actually this is the end of the block itself. Okay, because and actually the final results are going to be these, right? Because this is the complete, say, shaped in our way gradients, both horizontal and vertical. Okay, well, and now let's get outside the loop, well, not the loop, the if else statement, and now what we're going to do is to eliminate the pixels, the pixel values that are in the boundaries. Okay, so why are we doing this? Because we want to avoid boundary effects. So let me explain in a second what that means. So let's zero out the gradients at the boundary pixels so that we can avoid boundary effects. Okay, so what do I mean by that? Well, remember that when we were working with the gradients, yeah, in multiple times the calculations relied on neighboring pixels. Okay, so remember the kernel that, for instance, the simplest case, right, the D. So in this case, what happened was that we were taking, so for these layers, say for these two, right, we were taking the left and right and top and bottom neighbors, and in order to calculate the say resulting or the result of the kernel application, right? The output of the kernel. And what happened was that when we wanted to perform that operation in the corners, okay, top left, top right, and so on, we faced the issue that the left or the right corner or the left or the right neighbor, well, it was empty, right, originally. So we needed to include padding. Yeah, we need to include padding in order to cover that. And what we did was to, as you can see here, we didn't specify what numbers to input in the padding, right? Because if we go to conf2d, in the PyTorch documentation, oops, what happened here? So, well, okay. So conf to the PyTorch. Okay, so what happened was that we didn't specify padding mode, okay, and by default that is 0. That means that right now our paddings are zeros, okay. So that is a problem. Why? Because what that implies is that we are going to compute inaccurate gradients nearby the boundaries, okay, because of course those gradients are being computed based on neighbors that are zeros, or based on neighboring pixels that are essentially zeros, right? So that is not useful information for our decoding, right? So we are going to get rid of those. The solution is that we are going to get rid of the gradients that are in the boundaries so that we don't face that problem, all right? So that's what we're going to do here. And for sake of comparison, let's print the say maximum values, yeah, and what we are going to do now is to get rid of those. Okay, so let's get rid of first the top row. Okay, to do that we simply say, okay, we're going to keep the first two original dimensions, and let's just we're slicing. Okay, we're slicing, and we're just slicing in the first row, and we're going to set it equal to 0, right? Because we want to get rid of this say set of gradients there. Okay, fantastic. Well, and remember that the computation of both torch.max and torch.gather is essentially based on n2. So if we set n2 certain rows and columns equal to 0, consequently we're going to get that the corresponding rows and columns of n2 max and gather are going to be 0 as well. Okay, so we just set the first row to be equal to 0. We're going to do now the same, but for the last row. Okay, and now let's do the same for the first column. So that means that here we're going to get all the rows first column. Fantastic. And finally, let's do the same, but now for the last column. All right, great. Yeah, this n2, and there we go. So let's have a look. Let's actually compare. Have this compared. Okay, so these are the maximum gradients originally, and we get zeros. So in this case we keep no information, so no image whatsoever would be displayed. Well, of course this is a this is a toy example, right? and we get this because in this case we have a 2 by 2 matrix, so it's stored in the 4D tensor. So of course, if we get rid of the first row column, last row column, we get all zeros, right? But let's just change this to a very simple example. So 3 by 3 instead of 2 by 2, and now we should indeed get one value as being kept, right? Because as you can see clearly here, we get rid of the first column, the first row, the last column, the last row, then the first column and the last column. All right, fantastic. So that is the purpose of these, say, part of the code. And now what we want to do is to actually say define say a complete gradient. What do I mean by that? Well, we right now have just du and dv, okay, computed, right? But now what we want to do is to be able to store those two together. All right, so basically what we're going to do is to concatenate them. All right, and so yeah, let's do that. But before, let's actually remember how can we concatenate with PyTorch. So torch.cat, and let's have a look at the example. So we see that it takes a tensor, well, or a sequence of tensors actually. It takes a sequence of tensors that is going to be actually a tuple, and then we need to specify the dimension that we want to, it's optional but is always useful, the dimension over which the tensors are going to be concatenated. Okay, so for example, here we have a 2 by 3, right? 2 by 3, and here we want to concatenate this 2 by 3 tensor with respect to the rows. So this means that this block right here is going to be concatenated with itself 3 times with respect to the rows. And of course, we can then do the analogous but with respect to the columns. Okay, that's how torch.cat works. So now let's proceed with our own problem. So let's do that. So what we can do now is just, yeah, let's define our gradient. So let's construct, right? Let's construct our gradient. So to do that, we define, say, okay, whole gradient, and we're going to say torch.cat, and here remember we need a tuple. Okay, so the tuple is going to be the u, and well, it's going to be du, and let's think about this. All right, so think that this part of the code is outside the if-else statement. Okay, this means that it's going to work. This needs to work as well if the say image is grayscale. So if we specify here do you gather, when we have a grayscale, it's not going to understand it because it's going to have the u pass and dv pass. So what is convenient here is to rewrite these two variables to be du pass and dv pass again. Okay, so I'm going to overwrite them, and I'm going to say du pass and dv pass instead. because in that way, again, the entire code will work regardless of the shape of the input tensor. All right, so there we go. So did pass? Did we pass? Okay, great. And now we're going to concatenate with respect to the columns, and we'll understand why in a second. Okay, so actually let's visualize this. Okay, this whole gradient, and yeah, let's have a look. Okay, and actually, to be able to identify if this is correct, like more easily, let's also print out the both du and dv. So here, say gathered. So I'm just gonna actually do the exact same thing here. So the gathered horizontal gradient. Okay, I want to print out this. All right, let's print out this once again in order to be able to compare. So there's a vertical and dv. Okay, so in this way we should be able to see easily. Well, we have indeed, you see the gathered horizontal gradient, this chunk right here, and the vertical, which is this one. Perfect. Great. So now that we have constructed the gradient, okay, that's the, say, one of the first most important parts. But remember that now what we need to do is with these gradients need to be passed through orient in order to end up with the oriented gradients as a result of these function, right? So in order to do that, well, we need to actually recall orient. Okay, so yeah, now what we need to do is we need to do forward pass on orient. Okay, and in order to do that, we need to introduce in the code the definition of orient and its layer, essentially, okay, and gradient. So we did that here. So let me just copy paste the part of the orient. So this part right here, we're going to utilize. Okay. Also outside the loop. Let's put it here before. Okay, great. So now we, well, first of all, need to adapt this as we're outside the class. Let's just write it as it is right now and see if it works. Okay, so great. So now let's do that forward pass, and what we're gonna do is, all right, we're gonna define orient gradients. So oriented gradients, okay? So oriented gradients are going to be equal to what? Well, to the layer. The layer is called orient. Yes, it's called orient right now. So let's call it like that, orient. And we're going to pass through this layer the whole gradient. Okay, whole gradient. And yeah, what we want to do now is to print the result. So let me just print the result. Oriented gradient, just to visualize for now. Gradients, yeah. Oriented gradients, yeah. Okay, let's see if it works. Oh, it doesn't. Oh, of course, number of orientations we need to define in here. Originally it was 9, great. Okay, variable data has to be a tensor, but got conv2d. So essentially, we are having as an input a layer instead of a tensor. So let's see why that is happening. Oh, okay, I see. You see, because orient right now is set to be equal to weight.data, which is a tensor, yes, but it has the same name as the layer. Watch out, because this needs to be specified differently so that it is not confused by these tensor, this weight tensor right here. So now it should work. Let's see. Oh no, okay, what's going on? So tensor object has no attribute weight. Tensor object. Ah, okay, because you see, this needs to be called layer. Because of course, if we change the name of the layer, of course, we need to extract properly the weights from the layer with the same name. Okay, great. So now it should work. Oh, tensor object is not callable. Why? What is going on? Oriented gradients. Oh, of course, because you need to change the name. You see, I mean, of course, sometimes you need to go slowly. Just go slowly. Fantastic, fantastic. So here we have these are our oriented gradients. These are our oriented gradients, and actually, yeah. So these are the gradients that the function that we wanted the function to output, because remember that what we introduced, the input of the function is an image that can be grayscale or 3D or RGB, and then what it needs to do is to first of all compute the gradients that are associated to that image, all right, and then what it needs to do is to then classify those gradients depending on the angle that is associated to them, okay? And that was done by orient. So we need to pass those gradients, or horizontal, vertical, or the whole gradient that contains both horizontal and vertical. We need to pass the gradient through the orient so that we can get our gradients classified with respect to its angular position. So with respect to the angle that they have or have been associated to. Okay, great. So now what we need to do is to, yeah, let's just print this. So the oriented gradients are the following. Okay. And also what we need to do is to print out the shape. So print and the shape. So shape of oriented gradients is the following. The gradients.shape. Oops. Great. And now let's put here space. Okay. Great. Okay, so you can see that these are our oriented gradients as we wanted to, and here at the bottom what we get is the shape of it. So y18, because of course we're gonna get one oriented gradient per number of orientation due to how we defined orient. Remember that for orient, we were taking into account both the positive and negative directions, right? Orientations. So this means that if we set the number of orientations value to be equal to 9, well, we also need to take into account their corresponding negative orientation. So hence we get 18 in total. We have one gradient per possible orientation of the, say, actual gradient. Okay, but yeah, that is all I wanted to discuss for this video. I hope it was useful, and I am willing to see you very soon.